Welcome back, A peeps! Alright, today we are talking about Module 6 in your textbook, and the focus here is on correlation and experimentation, so let's just jump right in. In psychology, the only research method that can establish cause and effect is experimentation. All the techniques we talked about last time, the descriptive techniques, can only find a correlation between two things, two variables. So when I say that, this is what I want you to keep in mind. Correlation is when this happens, this also tends to happen. Notice that they're parallel, right? They're not touching. So experimentation seeks to find a cause and effect relationship. So that would be this causes this. So they actually intersect. That's how I imagine it in my mind. Correlation is a parallel. They go, if this increases, this also increases. Or if this increases, this tends to decrease. But there's a certain relationship, but not necessarily cause and effect. Experimentation is this causes this. These are some of the design terminology that you're going to need to know about experimental design. And this is very important for your FRQ on the AP exam. Starting in 2019, the College Board decided that every year, one of the AP Psychology FRQ questions will always have to do with research methods. And so all of these terms that you see listed here, we're going to discuss as a part of experimentation. And you'll need to know all of them, what they are, how they work, and how to do some of these things. So we'll go through these together. So let's do this through an example experiment. Let's say that we want to study the effect of food on learning. So I'm a teacher. Let's say I want to see if food affects learning. So that's my general hypothesis. If I want to study it, I need to be a little more specific. And I need to do something called operationalizing, or creating an operational definition. An operational definition or variable is basically how are we going to measure that? So when I say learning, what do I mean, right? Am I going to measure learning by performance on a test or quiz scores? Am I going to measure learning by how confident a student feels about a subject? So there are different ways that you can measure that. And when you do an experiment, you have to tell us how you're going to measure your variables so that if we want to replicate your experiment to see if we get the same results, we can measure that variable in the same way. So we might come up with a specific hypothesis like this one. Students who eat an oatmeal raisin cookie. So what do we mean by food? We're operationally defining food as an oatmeal raisin cookie. We're specifically saying in this case, food means an oatmeal raisin cookie. And then we'll say students who eat an oatmeal raisin cookie before class each day will have a higher average score on the semester final than students who don't eat a cookie. So then we're operationally defining learning as scores on the semester final. That's how we're going to measure whether students learned better or not. So in this case, you could do this different ways. Maybe you in your experiment, you want to do chocolate chip cookies, okay? That's another way to operationally define food. Maybe you just operationally define food as a sandwich. Okay, so there are different ways that you can measure that. Then, as same thing for learning. Maybe instead of an exam score, you want to ask students how confident they are in explaining that to somebody else. So that's how you're going to measure learning, is a rating. So they might say on a scale of 1 to 10, how confident are you in this subject now? And so you're going to collect those as your way of measuring learning. So then we need to define our variables. What are the variables in our experiment? Now this should be a little bit of review for y'all because you've studied in science, the scientific method, and you've probably talked about these terms. So first we need to figure out what is our independent variable. An independent variable is the cause, okay? It's this caused this. The X causes Y, X is our independent variable. It is the variable that is controlled by the experimenter. So in this experiment, what would the independent variable be? I want you to think about that for a second. So pause the video and take a second. Which of the variables in our hypothesis here is the independent variable. And we're back. Okay, so you should have thought about what you think the independent variable is in this experiment. So what causes a change in the other variable? In this experiment, that is going to be the cookies. So if you said cookie, that is correct. Eating cookies before class is our independent variable. It is what is controlled by the experimenter. The experimenter controls who gets the cookie. So then we need to figure out what is the dependent variable. And I like to think about it in the sense of it depends on the other variable. So the dependent variable depends on what the independent variable is doing. So it is what we're predicting. So as an experimenter, what are we predicting? What is the effect? So eating cookies is going to influence what in our experiment? It's supposed to influence, think about it. If you said the scores on the exam, then you're correct. So that's our learning, right? Food influences learning. So eating cookies influences, will lead to higher test scores. So the effect variable, the score, is our dependent variable because the score depends on whether the person got a cookie or didn't get a cookie. So let's say that we're doing this experiment. We've designed it. We know what we want to study and how we want to study it. Now we got to do it. The best thing you can do when you're answering an FRQ or a multiple choice question about psychological experimentation is to put yourself in the shoes of the experimenter. If you were actually going to carry this experiment out, what would you have to think about? How would you have to define things and set things up in such a way that it works out objectively? So one thing you have to do is you have to select what we call the experimental group. The experimental group is the group that receives the treatment, and the treatment is just the independent variable. So in this case, the treatment is getting a cookie to eat before class. So the experimental group in our experiment is the group of students who receive the cookie. So let's say if I wanted to do this, I, separated the class randomly into two groups, and one group gets a cookie and the other group doesn't. The experimental group is the one that gets the cookie. So we're going to say hypothetically that the experimental group got the cookie and they all got a 95% of them passed the exam. Then the other group that doesn't get a cookie is called the control group. They're the control group because they're the one that isn't getting, it's just normal. Nothing's happening out of the ordinary for them. They're the ones that don't receive the treatment so that we can compare. And if there's a difference between the experimental group and the control group, then we can infer that that might be because of the treatment, in this case, whether they got a cookie or not. So the control group will not get a cookie in this experiment. And let's say hypothetically that the control group, 82% of them pass the exam. Well, now we see a difference, right? There is a difference between the two. But we don't necessarily know that that is because of the cookie or not, okay? So we need to be careful about that. There are other things that might have caused a difference in the scores, and we have to think about that as the experimenter. These are the moles, okay? The moles that we mentioned earlier with our whack-a-mole example. And when you think of moles, the official term for that is what we call confounding variables. A confounding variable is something of an outside variable that has nothing to do with the independent or dependent variable that could influence our results in some way. So take, for example, the first example here, environmental variables. Maybe if I had the experimental group take the test in my classroom, but then the control group took the test in the library. Those are two different places. Maybe the experimental group, they could focus better because it's a smaller room, less going on, so their score was higher, maybe because of the environment, not because of the cookie. The control group maybe got a lower score because they were in a much bigger space with more people in the background, maybe more distraction. There are a lot of different things that can be confounding variables. Another example, let's say individual differences. Maybe my experimental group, even though I chose them randomly, maybe a high amount of the people that randomly ended up in that group are just really good studiers. They have great study habits, and so they scored higher on the test because they studied more, and the control group didn't study as much. So do you see, in both cases, these confounding variables are the reason for the difference in the scores and not the cookie. So our job as the experimenter is to try to prevent any of this stuff from affecting our results. Well, how do we do that? This is what we call controlling for outside variables. Well, there are different ways you could do that. If you want to prevent individual differences from influencing your results, that's why we choose people at random, right? If I said, okay, we're going to split the class, boys and girls. Boys are going to get a cookie, girls are going to not get a cookie, and we'll compare their scores. Well, there's nothing to say that maybe it's a gender thing. Maybe the girls score higher on that test than the boys, and it's because of their gender and not because of the cookie. All right, so that wouldn't be a smart thing to do. That would be a flaw in my experiment. A better way to do that would be to have a mixture of both boys and girls and people of different ages, etc. So this is why using a random sample is so important. So I like to think of the confounding variables are like the Darth Vader of experimentation. They are our nemesis. So what are some ways we can specifically control for these different examples? So I already told you a little bit about individual differences. If you're looking at the environment as a confounding variable, you would make sure that you have the same environment for both groups. That way, that isn't a factor. It cannot mess with your results. If they both take the test in the same room at the same time of day, with the same conditions, then you know that any difference in scores is not due to the environment because they had the same environment. Same thing with expectations. Maybe one group was expecting to do better on the test than the other because maybe I talked them up before. Okay, so in this case, you would want to use what we call a blind procedure. This means that they don't know what is being studied. They don't know what the experiment is. They don't know that it has anything to do with the cookie. Okay, so nobody knows what to expect. That eliminates expectations and the influence they can have on the way they perform on the test. So we're going to reiterate one term we've already learned and add another one. This is another confusing pair that is very common in this class. So you need to be able to tell me the difference between random sampling and random assignment. Random sampling is just choosing a participant out of the wider population of what you're studying. So remember our example of if we want to study MacArthur students. What's our population? It's all MacArthur students. So if we want to do a study, we can choose randomly 100 students from the whole school, and that's going to be our sample. So the population is every student enrolled at Mac. The sample is our 100 random kids that we choose, and we can do that out of a hat. And like we showed with those jars, you can use that to generalize as long as it's random. So you're just picking a small group out of the wider population. Then let's take that small group, that sample that we've already chosen, and then we need to divide that group into two groups, our experimental group and our control group. So this is what we call random assignment. Because within the 100 kids we chose from all 3,000 max students, we still want to divide them into those two smaller groups randomly so that we don't end up with, all AP kids and all non-AP kids. So we're going to divide them into control versus experimental group randomly as well. And this will prevent individual differences like personality type, age, level of course from affecting our data. If you can't randomly assign people to groups, you are not conducting an experiment. So this is essential to experimentation. There's another thing that we need to keep in mind when we look at the results of our fake experiment here. So if you look at our numbers here, we have our experimental group, 95% was the average score. I think I said 95% passed, but I meant the average score in the experimental group was a 95%. And then in the control group, it was an 82%. So there is a difference. The question we have to answer as scientists, though, is this a big enough difference to make it what we call significant, right? So is that a big enough difference that we can say, okay, cookies really do influence learning? Or would it be better if they got an 85% average? Does that mean that there's not much difference? Is that a big difference or a little difference? That's kind of subjective, right? What if their average was a 93%? Well, then it's not that different, so we might not say that our results are significantly different. So it's hardly ever going to be exactly the same. The question is, at what point does it become a significant difference between our results? So this is something that we would call statistical significance. There is some way that we can determine whether our results are what we call significantly different. So the way that we look at statistical significance, which we'll talk about in detail later, is we can calculate something called the p-value. Now, don't panic. Okay, if you are not in AP Stats, you do not have to learn how to calculate the p-value, because that's not what we're all about here. You can do that in college if you want to pursue a career in social science, and you have to learn how to do that. For now, we're going to talk about what it means, and we're going to talk about how to interpret a p-value. So we'll pretend we're going to let the imaginary statisticians calculate it for us, and then we're just going to have to learn how to tell what it means. So the p-value tells us the likelihood that a result was caused by chance. So what is the likelihood that the results we got in our experiment were just a fluke? So the way that we can determine whether we consider it to be significant, and this is a number that's been agreed upon by scientists, is that it cannot be any higher than 5%. And that, as a decimal, is 0.05. So in other words, p must be less than or equal to 0.05 to be considered statistically significant. So we'll come back to statistical significance later. For now, I want to stick with the basics of experimental design. So one of the terms I mentioned before is operational definitions. And right now I want to emphasize what those are and why they're important. So let's do another practice experiment. Let's say we want to study how many students are likely to smile for their senior photos. So we might come up with a hypothesis that says students are more likely to smile for their senior photos if they have a friendly photographer. So in this case, our independent variable, the variable that is controlled by the experimenter, is how friendly that photographer is. So if we're the experimenter, we might have our experimental group in a room working with a photographer who's especially nice and friendly, and then our control group will be in a room with a photographer that's kind of, closed off, not very kind or friendly, and just kind of, all right, 3, 2, 1, go. All right. So then our dependent variable, the variable that's going to be affected by the level of friendliness of our photographer, is whether or not the students are smiling. The question, though, is how do we define smiling? So let's try this out. Look at the photographs on the next slide. And I want you to count and tell me how many smiles you think you see. So out of these 6 photos, how many of these students are smiling? And you can pause the video to have a little bit more time. Okay, so when we do this in person, I always get different numbers from everybody. Why do you think that is? Well, one person might say a smile is showing teeth. So if that is how we are defining a smile, operationally defining, if that's how we're going to measure what a smile is, then only 2 of these students are actually smiling in that case. But let's say we operationally define it as both corners of the mouth are turned upward. Well, then we would count a few more, right? We might count this person, this person, this person, this person, and then we might debate about these 2. So it's very important that when you do an experiment, you have to decide how to measure that variable. If you are reading about another experiment, then you have to look for how did they operationally define that variable. So in this case, if you're reading an article that says 50% of students smile more when they have a friendly photographer, then the first thing you should think of is, well, what did they count as a smile? Because that's subjective. You have to tell us how are you measuring that variable. And it doesn't matter which one you choose, just so long as you communicate that in your results so that everyone can see, okay, in this experiment, they only counted teeth showing. So that's going to change my expectations of what they mean by a smile. So you always want to ask, how were the research variables operationalized in an experiment? This is where that skepticism comes in, because you need to know what they mean. If you see, on the MacArthur sign, U.S. News, best schools. Well, how did they define best school? Did they define it by percentage of graduates? Did they define it by STAR test scores? Did they define it by, student ratings of how much they enjoyed it? So that's different. Learning, happiness, these are all very abstract things that you have to put in measurable terms if you're going to do an experiment. So research cannot be replicated unless we have an operational definition. Because let's say I do an experiment on how a photographer's friendliness affects smiles, and I define smiles as teeth showing, but Miss Woodward next door to me does the same experiment, except she counted smiles of anyone with both corners upturned. Well, even if we got the exact same pictures as our results, we would have different numbers. And so we can't replicate an experiment unless we have those same operational definitions. Okay, now we're going to talk a little bit about correlational research. So remember, correlation is not cause and effect. Correlation is if this does this, then this will do either this or that. So if X increases, Y increases. Or if X increases, Y tends to decrease. There's a relationship, but we can't say that X causes Y. So correlation measures the strength of the relationship between two variables. It can be positive or negative, and mainly it's useful for us to make predictions. So let's talk more in depth. Let's look at some examples. But first, here is your mantra for the year. I want you to ingrain this in your heads, okay? I want you to hear me saying this in your sleep. I'm going to haunt you. Okay, so correlation is not causation. So just because an increase in watching television has a relationship with a decrease in test scores doesn't mean that watching television makes you dumber, right? It just means there's a correlation. We can't say that it causes it necessarily, all right? So there is a relationship, but that's all we can say. It is not causation. Say it again. Correlation is not causation. And again, correlation is not causation. Okay. So what does correlation look like? There is a visual representation of correlation that you are going to see, and you need to be able to interpret it. So we tend to represent correlation visually by using what we call a scatter plot. And you're probably familiar with these. So you'll notice on the bottom here is our X variable and here is our Y variable. So if we have a positive correlation, the scatter plot will look like this. There will be a slow increase. As X increases, so does Y. If we have a negative correlation, then as X increases, Y decreases. So I like to use my hand signals to practice this. So a positive correlation is if X increases, Y increases. Negative correlation would be X increases, Y decreases. What if there's no correlation between the variables at all? Well, then you're just going to see a bunch of dots everywhere. It's going to be no trend anywhere in that graph. So they are not going to line up a certain way. Okay, so now I want you to practice this. So in your notes, you should have some scatter plots, and I want you to draw a graph that represents a perfect positive correlation. So think back, what is a positive correlation? And if it's perfect, then that means that it's perfectly balanced. So consider what that might look like. And you can pause the video and draw your graph. Okay, and we're back. So let's see how you did. Your graph should look something like this. So notice that unlike just the positive where it was a little bit spread out, but it was mostly trending upwards, this is a perfect line, right? So if x increases by 1, y also increases by 1. So this is what we call perfect positive correlation. If there was a little slight deviation from the line, then it would just be a positive correlation. All right, now draw a graph that represents a perfect negative correlation. Pause the video and draw your graph. And we're back. So let's see how you did on this one. You guessed it. It is basically the opposite of the last graph. So as x increases by 1, then y decreases by 1. So it's just going in the opposite direction, but it's the same basic idea. The perfect correlation is that there's an equal amount of change. So then how do we express correlation numerically? So there is something that, again, if you are in statistics, you'll learn how to calculate, called the correlation coefficient. And this is represented by the letter R. And it will look something like what you see here. Now, correlation, it's going to be a number between -1 and +1. It cannot be lower than -1 or higher than +1. And so when you see the number, there are different parts of that correlation coefficient that tell you different things. So for example, if it's positive or negative, that's going to tell you the direction of the relationship. So remember, we just practiced positive correlation looks one way and negative correlation looks another way. So if it's positive, that tells us what direction the correlation is. Are they going the same direction? If they're going opposite directions, that's a negative correlation. Then the number itself is going to tell us how strong the relationship between the two variables is. So that's going to be 0 to 1. If 1 is the highest and we have 0.37, you can think of it like a percentage. It's about 37%. So that's closer to the lower end, right, of strength. So it's not that strong. Now, let's say the number is negative 0.37. Which is possible. That's about the same strength, it's just going the other direction. So then if we want to guess a strong relationship, if we have a number that represents a strong relationship, it'll be closer to 1 or -1. So if this was positive 0.95, that's a very strong relationship. If it was negative 0.95, that's also a very strong relationship. It's just a strong negative relationship between your variables. So this is a great visual for understanding how all of that works. If the middle of our spectrum here is 0, then the further you get from 0 to either side, the stronger the relationship gets. And then it just depends. If you're above 0, you have a positive correlation. If you're below 0, you have a negative correlation. All right, guys, so we're going to practice plotting correlation coefficients. We're going to start with a correlation coefficient of positive 0.21. So before we draw, let's point a few things out. First off, we see that this is positive, so we know that our line is generally going to move upward from left to right. Next, we should point out the number that we have going on here. And when you think back to our number line, we know that correlation coefficients are any number between -1 and 1 with 0 in the middle. So if we're positive, we know we're on this side. And we're 0.21, so we're closer to the 0 here. And what this tells us is that we have a weak correlation because we are not very close to the edge of our spectrum here. And when it's weak, then when we plot our points here on this line or near the line, our points are actually going to be spread out pretty far from the line. So it'll look something like this. Generally trending upwards, but not very close together. And that's our scatter plot. Okay, now we're going to plot a correlation coefficient of R equals -0.97. So the first thing we notice here is that we are negative, so our line is going to trend downward from left to right. So we'll just draw a little reference arrow here. It's not very straight, but no worries. Next thing we notice is that our number is very, very close to -1. So it's going to be on the edge of our number line here, pretty darn close to the edge, which means that this is a strong negative correlation. If it's strong, then when we plot our points, they're going to be fairly close to that line. In fact, they're so close because it's almost perfect. Next up, we are going to plot a correlation coefficient of r equals positive 0.89. Right, first off, we know it's positive, so our line is going to trend upward from left to right. Here's a reference. Then we notice our number here is very close to +1. So we're probably around here on our number line, which means this is fairly strong. It's not as strong as it could be, but it's leaning towards a 1. So that means that all of our points that we're going to plot here will be pretty close to that center line. Not as close as the last one, but pretty close, enough that you can clearly see a trend. And there it is. All right, next up we are plotting a correlation coefficient of r equals -0.37. So the first thing we notice is that we're negative, so our line is going to trend downward from left to right. And then we notice that we have 0.37. So on our number line, we are going to be to the left of 0, but not very close to -1. We're going to be closer to 0. So we've got a fairly weak correlation here, which means that the dots, when we plot them on our scatter plot here, are not going to be very close to the line. So we'll just draw a quick reference line, and then we'll get our dots, and they're going to be more spread out. Still trending downward clearly, but not quite close together. And there you go. All right, finally, we are going to plot a correlation coefficient of r equals -1.2. So the first thing you'll notice here is that we're in the negative, so our line is going to trend downward from left to right. Next, you'll notice the number that we have here is on the higher end. So, well, wait a minute. Our number is 1.2. It's going to be out here. But we know that the lowest correlation coefficient number can go is -1, and the highest is 1. So guess what? This is an invalid correlation coefficient. It is not real. Ignore, delete, abandon.